Math 1332, Chapter 2, Set Theory, Section 3, Using Venn Diagrams to Study Set Operations, Video 4, DeMorgan's Law. And this really should say DeMorgan's Laws because there's two of them. Now, I could just say here they are, but I really want to try to get you to see where this comes from instead of just saying, oh, look at this nifty result. So I've got a situation set up here that's similar to one from a previous video. We're going to let U be the set of all doctors. We're going to let P be the set of all pediatricians, and F be the set of all female doctors. Excuse me, some bad grammar there. I put the word all in after the fact. I just put it in the wrong place. All right, so U is the set of all doctors, P is the set of all pediatricians, and F is the set of all female doctors. We could easily draw a quick Venn diagram for this. We just need to set up a couple of circles, have our universe here, and we could say that this circle represents the pediatricians, and this circle represents the female doctors. Notice I use letter choices that make sense here, P for pediatrician, F for female. All right, let's start by describing the elements of P intersect F. If I can type. All right, well, this is pretty easy because you may recall when we talked about verbal descriptions of sets that the intersection can be translated to the word and. So if you belong to the intersection, you have to be a female and a pediatrician. So P intersect F would be the set of female pediatricians. Now, that's not the only way you could describe it, because if you notice, I didn't use the word and. So how could we describe them using the word and? The set of doctors who are pediatricians and females. Again, I only wanted to try to describe it using the word and because intersection is associated with the word and. But what about the second one? Describe the elements of the complement of P intersect F. So let's think about this in terms of people in a room. We've got a building with all the doctors in the world in it. And we open a door and we say, all right, we need all the female pediatricians to come into this room. Okay, you got that in your mind? All the doctors in the world in a building, we open a door to a room and invite all female pediatricians into the room. That's the contents of P intersect F. The contents of the complement of P intersect F would be the people who did not come into the room. So how would you describe the people that did not come into the room? Are they non-pediatricians? Well, not all of them, because some of the pediatricians didn't come into the room. Are they all males? Well, not all of them, because some of the females didn't come into the room. Who came into the room? The people who are both pediatricians and females. So how could you describe the people outside of the room? People in the complement. The set of doctors who are not pediatricians. But that's not sufficient because there are some pediatricians out there that just happen to be male. Set of doctors who are not pediatricians or not female. Or possibly both. Remember, it's the inclusive or here. So you have to be a little more cautious in describing the complement of this intersection because the people outside of it aren't necessarily all males and aren't necessarily all non-pediatricians. If you're not a pediatrician and you're a male, if you're a male pediatrician, then you're outside of the room. If you're female, but you're not a pediatrician, then you're outside of the room. Remember, the only people that went into the room were the female pediatricians. And so the complement is who didn't go into the room. Now, why did I bring all this up? Because I want to look a little bit more closely at the way we answered the description of the complement. Not pediatricians or not female. If we were to translate that back into symbols, I know exactly how to translate all three of those pieces. Not a pediatrician means complement of P. Or doesn't mean intersection, it means union. Not female means complement of F. We described this, but our description almost describes this, which raises the question, are these equal? And the answer is yes. They're equal because that is one of two laws called DeMorgan's laws. So let's see what those are. The first of DeMorgan's laws is pretty much what we just said, that the complement of an intersection and the union of the complements are equal. The complement of an intersection, we'll say A intersect B to be generic, is equal to the union of the complements. And we can actually write that in words by writing exactly what we just said. The complement of the union, of the intersection of two sets equals the intersection of the complements of the two sets. I know it's a mess of words, but it's precisely just that, words. I don't think I can get this on one line unless I do something a little sneaky that I don't want to do, but I will. We'll take the font size down. The complement of the intersection of two sets equals the intersection of the complements, and that's not correct either. Union of the complements. And now it makes me wonder if I can put it back at a 24-point font, and I can. Where's my period? There it is. All right. The complement of the intersection, that's the left half. The complement of the intersection, whoa, that's not highlighted. That was covering. Complement of the intersection of two sets, that's this, is equal to the union of the complements of the two sets. Now, why bring up DeMorgan's laws? We'll get to the second one in a second. Because there's something that people want to do that is wrong. They'll see something like this, and for whatever reason, their brain kicks into the distributive property. You might recall the distributive property from algebra that says something like 5 times x plus 4. You distribute the 5 and you get 5x plus 20, something like that. But for some reason, people's brains want to go, oh, well, if I have a complement outside of here, I'll just give it to everybody. Problem is, that's wrong. Looks good, but it's wrong. Unless you also think about distributing the complement to the intersection. And although it's not really a true statement, the complement of an intersection, or the opposite of an intersection, if you will, and even that's not true, is a union. So if you think about it as giving the complement to everybody, but the complement turns the intersection sign upside down, then I guess you could look at it from a distributive nature. But it's not really a distributive property. DeMorgan's law is really a counter to a claim of a distributive property. But that's the first one. The complement of the intersection equals the union of the complements. But what's the second of DeMorgan's laws? Well, the second of DeMorgan's laws, I'm not sure what's going on here. There we go. The second of DeMorgan's laws is actually almost exactly like the first, which is why I just copied that. The only difference between the first and the second is the words intersection and union trade places. So let's see if I can, no, it won't let me drag and drop here. So let's put union where the word intersection is and intersection where the word union is. And let's see if we can write this in symbols. All right. So let's start with the, we'll highlight this one in pink. Let's start with the complement of the union of two sets. How would we write that? Well, complement of means we start with this. But we're taking the complement of more than one set, so we have to put it in parentheses. Complement of the union of two sets. That would be the left half of the second of DeMorgan's laws, is equal to, and let's see how we would write symbolically the second half of this. Intersection of the complements of the two sets. All right, I think I can do this. Intersection of the complements of the two sets. And we'll go ahead and highlight that orange to match it up with those words. And just like the first of DeMorgan's laws, this one is kind of a distributive property. If you have the complement of a union and want to distribute it to the sets, you kind of also have to distribute it to the union sign in the middle, but the effect of it is it turns it upside down. It's not really a distributive property, but it's gimmicky enough to help remember what DeMorgan's laws are. Now, why is this useful? The reason it's useful is sometimes it can make evaluating set operations a little bit easier. For example, let's say that we were asked to evaluate this, and I just realized that I'm about to paint myself into a corner that we're going to get out of real quickly. Let's say that we wanted a Venn diagram for this, the complement of the intersection of A and B complement. Well, according to DeMorgan's laws, because we have the complement of an intersection, we can distribute it, but we also have to change the intersection sign. So we get the complement of A, flip the intersection sign to a union sign, and we get the complement of B. And here's the corner I've painted myself into that I'm about to get us out of. We haven't talked about what it means to be the complement of a complement. We'll do it real quick with a real quick Venn diagram. Here's U, here's B. B complement means outside of B. So we'll shade in the outside of B. This is B complement. But the complement of that means the outside of that. So what's the outside of B? It's the inside. In other words, the complement of a complement is the original set. And this is something that we didn't talk about before when we talked about complements, but it really kind of makes sense because complement means go outside of something. So let's say that you're in a building and you're in a room and you want to go to that room's complement, then you would go outside of the room. But let's say you want to go to the complement of the outside of the room, then you would have to go back inside the room. Another way of thinking about it is that a complement is like a double negative. They cancel each other. So what does that mean here? That means if we were doing DeMorgan's law on this expression, we wanted to know the complement of the intersection of A and B complement, then DeMorgan's law says, well, you're being kind of redundant because we can give the complement to each half and turn the intersection sign upside down. So we get A complement union, the complement of B is just B. So which of the two do you think would be easier to draw a Venn diagram for? This guy, which has three operations. The operations are intersection, complement, complement, or this guy that has two operations. The operations are complement and union. Granted, it only takes it down one notch in terms of the number of operations, but simpler is better. All right. So yeah, DeMorgan's law is really, let's just go back to him real quick, and I want to take out all the highlighting because they're really kind of crowding everything up. Let's see if I can do this without accidentally killing any words. And let's get rid of this garbage down here. It's not really garbage, it's just a gimmicky way to remember DeMorgan's laws. But DeMorgan's laws simply say what you can do when you take the complement of a union and an intersection. So in closing, the first of DeMorgan's laws is, and I'll highlight it as I say it, even though I just got rid of the highlighting, the complement of the intersection of two sets equals the union of the complement of two sets. And the complement of the union is equal to the intersection of the complements. Actually, there is one thing I want to close with this. The number of sets is irrelevant. meaning that as long as it's unions or complements, if I had something like A union B union C complement, DeMorgan's law would still hold in the sense that you could distribute the complement to everybody, but all the unions would become intersections. But it has to be all unions or all intersections. It can't be a combination of the two before you turn them upside down.